So here we are. We're in the home stretch. Just a few more lectures now. And we are with this last sort of mini block, returning to circuitry. We're going to take everything we learned about magnetism and see how it informs our ability to do circuitry and sort of some of the new circuit elements and how those combine with our old knowledge of circuitry. And what you're seeing here is a demonstration of some of the applications of some of the magnetic properties we learned in the last block. Notably here, notice that the egg is not cooking directly on the surface of the stove, only the bit of pan that is connected to the stove. That means that somehow this stove is making this pan get hot without the stove itself getting hot, because otherwise the egg would just cook right on the stove, like a normal stovetop that cooks by just getting very hot. Now, we've seen this, and we know that that has something to do with the stove's ability to incite electron movement in the pan. And we'll see how exactly that's possible, even though there's no sort of open circuitry available here. So today we're going to take our knowledge of magnetism and move it to circuitry with this idea of inductance, sort of taking Faraday's law and seeing how we can insert it as a component in circuitry. And I want to open this up by sort of communicating an idea. What if I had a pair of coils of wire? So these are two circular loops of wire, and one has nothing connected to it. It is literally just a circle of metal. But it is held above another circle of metal, which has alternating current driven through it. So it has a sort of battery source here, which forces current, which is described by a sine wave. So that means current is going to be bouncing back and forth. Sine oscillates. And what is the effect of putting alternating current in this bottom loop? What effect is that going to have on the top loop, if any? Well, we know that if we generate alternating current, sort of oscillating current in the bottom loop, that current is going to, since it's moving in a loop, create a strong magnetic field at its center. And since the current itself oscillates, then of course the field that it creates will also oscillate, because when it's moving clockwise, it points in one direction according to the right-hand rule, and when it moves counterclockwise, when sign switches to minus sign, then the field will switch into the other direction. Now, this field will pass through the top coil since it is held very close. If this top coil were off and away, nothing would happen. And since we have alternating field creating alternating flux, we know that by Faraday's law, that's going to induce voltage, which creates current, and we'll now have current creating its own field to oppose the change in flux. But the sort of main property I want to identify is the fact that I was able to generate current in the top coil despite not even touching it at all, which is a fantastic property. Just by alternating current in this bottom loop held close to the top loop, that created a magnetic field, which was felt as flux, which through Faraday's law created current in the top loop, all without any actual circuit connection between the two, just with the ability for them to share magnetic fields from one to the other. And that's an incredible property of transferring current and transferring this sort of circuit knowledge that we have without needing a complete connection, without needing to touch. And there are so many sort of important applications of this, including the one we saw with the opening, that the stove is able to transmit current from its circuitry to now what's kind of a primitive circuit, being the pan, without actually touching, without needing some hot or electrical interface that would be maybe dangerous to touch, or even would just get hot in the least bit to cook an egg. This is useful in the design of toothbrushes, because if you need a means to charge an electric toothbrush, you'd prefer to not do that with any open wires, because when you handle a toothbrush, it tends to get wet, and if you put open wires near water, bad things happen. So this gives us a means to sort of transmit current from the bottom plate up into the toothbrush itself without actually needing some open connection, and you can cover everything with nice waterproof plastic. If you've seen these before on electrical wires, these are transformers. These transmit the incredible voltages, just the absolutely ludicrous amounts of power that we carry in power lines down to circuits that are usable on a more home wiring setting, because you can absolutely not plug these incredible power lines directly into your home wiring. These transformers sort of allow you to get from one to the other without needing to tap directly into this incredible power source. And then the last sort of kind of funky application of this is if you've ever noticed these odd lines in the pavement next to a traffic light, these are what allow the traffic light to sense the presence of your car. That underneath the pavement here is a coil of wires that when your car drives over it, it senses this sort of change in the electrical behavior with the fact that there's now something on top of it for it to interact with. And we'll see that it measures that as inductance, and what's happening is every time your car drives over it, it is sort of noticing that change in inductance. It is not a pressure plate, it is purely an example of what's going on here with this circuit behavior. So we call this mutual inductance of sharing from one to the other, but could this happen on its own? Could we have a kind of interaction between magnetic field and current like this for just one solenoid on its own? For instance, in this scenario, what would happen if I turn the battery on? Well, the battery, after we sort of just connect it, would attempt to force a bunch of current through this circuit. But going from no current in the circuit to lots of current in the circuit means going from no magnetic field through this solenoid to now suddenly lots of magnetic field, because this current moving in a circle generates magnetic field. And we've seen this as that's sort of the whole point of what these solenoid configurations are. That's what these coils of wires are called, is that they generate giant magnetic fields. So trying to now suddenly change the current and change the magnetic field through this would, through Faraday's law, induce an opposing voltage to stop that behavior, what's called a back EMF, to try to oppose that. And in particular, how much current you're allowed to pass through at some voltage. So if you apply some battery voltage to this solenoid, exactly how much current you're allowed to put through is called the inductance. And we call it L. Now, what you're seeing here is basically an application of Faraday's law. It's saying the voltage is the time derivative of the flux, where we have done some Biot-Savart calculation to relate current to flux here, and we've sort of reassigned the derivative through there. Now, that is a complicated calculation, but we can actually kind of treat this definition here of what we call inductance. We can just treat this like another relationship, like Ohm's law, V equals IR, and the capacitance definition of Q equals CV, as just a ratio, where Ohm's law is the ratio of how much voltage you apply to how much current you get out. Q equals CV is a ratio of how much voltage you apply versus how much charge you're able to store. Effectively here we're seeing yet another definition like that, where how much voltage you apply versus how much generated current you're allowed to force through, specifically the rate at which you're allowed to build up current. For something with very large magnetic fields, you would expect that it's very hard to start forcing current through that, which would make it a large inductance, meaning that sort of lowering how much change in current you're able to get for some amount of voltage. So treat this like another ratio type definition, like Ohm's law and the capacitance definition. The units for inductance, if you convert sort of voltage on one side and amps per second on the other, are what we combine to be henries. So what determines inductance? What would, thinking now inductance, if we think of it from that ratio as a purely conceptual object, we think of it as a measure of how hard it is to change the current through some solenoid or through some bit of circuitry. Just like we could think of resistance as a measure of how hard it is to put current through something. This is a measure of how hard it is to change current through something. And given that it's sort of steeped in the magnetic field, we could ask, when you design a solenoid, making it hard to change current through that solenoid sort of is a relationship of how big are the magnetic fields through that solenoid. And what would determine that? Well, one, the number of loops. More loops means more where each loop creates its own magnetic field. That's more magnetic fields, of course. The area of the loops is probably going to have some effect, though it's not clear sort of on the outset what effect it's going to have, because we know bigger loops increases the radius, sort of decreasing the strength of the magnetic field, but bigger area also makes for bigger flux, potentially making a bigger interaction with Faraday's law. So we're not exactly sure what the effect of the area is going to be. And then the length of the solenoid, kind of surprisingly, is going to make a difference as well, where maybe you think length being longer is bigger, but it's actually the opposite, because if you take the same number of coils and sort of stretch them out over a larger length, you're spreading out the effect of that magnetic field, where you actually want them to be as compressed in and tight as possible to sort of condense and magnify that magnetic field effect. So more loops being more flux, area being weaker field but more flux, and we'll see who wins there, and then length being the spreading out of the B field. All of that comes together in a formula which is possible to derive using Ampere's law, but I'm going to sort of opt not to worry too much about the derivation of this formula. In fact, we won't use it a lot. I think I'm more interested in the conceptual behavior being demonstrated here. And the important pieces to pick out were that indeed everything sort of went as we expected with the number of loops and the length, that more coils was more inductance, bigger fields, more length was less inductance because it's spread out, and then it turns out that the area has a direct effect on the inductance, and it's proportional. The reason there is that if you think of radius determining the area, radius only affected the Biot-Savart law in one power, but it affects the area for the flux as pi r squared, so that squaring sort of wins out. And then the other factor which comes up is the medium, that oftentimes you'll see in engineering an attempt to increase the inductance by inserting iron sort of in along the center of your inductor to wind up creating bigger magnetic fields, because we know that these permeable materials increase the sort of size of the magnetic fields along the solenoid. So that's another way to increase inductance. Why don't we take a moment here to do one of our checkpoints and see if we can put some of our basic understanding of this new definition for the inductance together with our ideas in Kirchhoff's laws. This is a bit of a trick question here, so take your time on it and see what you think. Pause it here. All right, welcome back. As funky as it sounds, I hope you found C as your answer. According to the loop rule, we know that the voltage on this inductor is just equal to the battery, which means that we have a fixed derivative of the current over time. That relationship tells us that the derivative of current in this circuit is constant. It says that for a circuit which looks just like this, all the inductor does is limit how you can build up current, but according to the math, that's just constant. So you would just have a constant slope, and your current would keep increasing forever. Obviously, that doesn't make a ton of sense, given what we know about circuitry. But what we're missing here is that we've sort of neglected that, of course, there's going to be some resistance at some point. You can't just keep building up current forever, when in reality, at some point, the more current you build up, the more power and sort of voltage is going to keep getting lost over the resistance itself of the circuit. Now, I am combining all the resistances here of the battery, of all of this wire here, and any external resistors into one big resistance because it's all in series. And I'm going to ask what happens here in a more realistic setting. Well, we again get the battery trying to force current through the circuit. And the first thing that happens is it says, you went from no current to lots of current. You can't just close this switch and immediately get current moving through, because that would be an instantaneous change in the magnetic field through this solenoid, which Faraday's law is, of course, going to stop. So Faraday's law says you have to build your current up slowly. But as current builds up more and more of your voltage is being lost over the resistor thanks to Ohm's law, which means that the battery is not trying to interact with the inductor as much, and it's more interacting with the resistor. And we sort of trade off that as this burns, battery is only able to add less and less current to the circuit, and at some point we sort of max out, and we cap out at the battery working entirely to fight against the voltage being lost over the resistor and no longer being able to add any more current across the inductor. And the inductor sort of relaxes and stops taking away voltage as we reach some equilibrium. And we wind up with the circuit sort of finding itself at a constant current. We'll see mathematically all the details of this behavior in the next video. We'll sort of treat this as another circuit, kind of like the RC circuit of a circuit that changes over time, which is clearly what this behavior here is suggesting to us. But for the moment, I want to stick with the sort of looser conceptual understanding and see if we can take advantage of this property that the inductor has of limiting the rate at which current can change in a circuit. That was sort of its behavior in the past two examples. Does that have any practical application for us? Well, let's say you have a circuit that looks like this, where you have the massive, massive currents coming out of power wires that you want to use to light your light bulb in your home. Well, if you try to just take power or try to take current straight out of a power line and dump it into your home circuitry, it's going to fry that circuit and completely overload your light bulb. That will burn out your light bulb completely. But if you run it through an inductor first, it will shrink the size of that current. And why is that? Well, the current is limiting the rate at which current can change. And with a gigantic oscillating current, that is clearly changing back and forth a ton. But passing it through the inductor says you can't make big drastic changes, so it limits the size of those changes. If you limit the derivative here, you're basically shrinking the function itself as well. So you get down to something a bit smaller that actually can be used on your light bulb without completely frying it. Now you may think, well, couldn't we have just done the same thing with a resistor? Resistors shrink the size of current as well. We've seen that all the time in our understanding of circuits. But doing so with a resistor is going to pass a ton of current through the resistor, making it get incredibly hot. And if you hook up a resistor to power lines, it's going to also be nasty. So the inductor is able to do that purely with the generation of magnetic fields, which don't get hot in any way on their own. And another application of these magnetic fields and this idea of storing magnetic fields in a circuit is that they are a means of storing energy as well. We thought of the capacitor back in the RC circuit as one of its roles in the circuit as being something that stores energy for later release, and it stored that energy in the electric field. Inductors actually do the same thing as a means of storing energy in the magnetic field. Take this circuit here, where if we let it hang out for a while and build up current, at some point it's going to reach that equilibrium current, and it's just going to be stuck there. And then what happens if I flip the switch? We can treat that as energy being stored in the magnetic field, which we would calculate with this formula. And upon flipping the switch, that current, without a battery, wants to just disappear. Now that there's no more electric field here pushing it around, there's no reason for those electrons to be zipping around anymore. But the inductor says you can't just take away current just like that, because that's going from lots of magnetic field where you have lots of current. If you try to take it away all at once, you're taking away all the magnetic field at once, and Faraday's law is going to induce a large voltage to oppose that. So it says in the same way that you had to build up current slowly on the inductor, you have to take it away slowly as well. And you can use that leakage of current, that sort of storing of excess current, to do some task. You could continue to keep a light bulb lit even without a battery, just by taking advantage of the sort of stored energy, the stored current in your inductor, which is a nice new application, kind of similar to how a capacitor would do much the same for us, at least temporarily. And we can use that as sort of a new means of energy storage with magnetic field now rather than electric field. So for the moment, we'll leave it there with our understanding of the inductor. We've sort of seen a qualitative approach to magnetic fields in circuitry and sort of introduced this new circuit element. And in the next lecture, we'll really dive into the math and sort of dive into the role that this thing can play in Kirchhoff's laws and our full sort of circuit analysis. And then we'll apply our RC circuit approach to the LR circuit now.